You know, there's something almost hypnotic about watching metal being shaped at incredible speeds, turning a rough steel billet into a perfectly engineered part in just minutes. And today, we're getting up close and personal with one of the most capable turning machines in modern manufacturing, the CTX Alpha 450 by DMG Mori. The CTX Alpha 450 is a CNC universal turning machine built for high-precision, high-productivity work. It comes equipped with a Siemens Cinemeric 1 control system, one of the most advanced CNC controllers in the industry today, giving operators seamless digital integration right on the shop floor. The machine features a 45-degree slant bed design, which dramatically improves chip evacuation and operator ergonomics. The main spindle delivers up to 5,000 RPM with 52 kilowatts of power, while the integrated motor spindle provides a torque of 610 Newton-meters, more than enough muscle to tackle tough alloys like titanium and Inconel. What really makes the CTX Alpha 450 stand out is its Tri-Fix quick-change tooling system. Operators can swap tools in under 30 seconds. No fumbling, no wasted setup time. The turret holds up to 12 powered tool stations, meaning complex parts with milling, drilling, and turning operations can all be completed in a single clamping. That's what the industry calls done-in-one machining, and it saves enormous time. The machine also features a Y-axis on the turret, allowing off-center milling and drilling operations without repositioning the workpiece. Bar capacity reaches 65 millimeters in diameter, making it ideal for medium to large batch production of shafts, flanges, and precision components. First, the raw bar stock is fed through the spindle and clamped automatically by the hydraulic chuck. The Cinemeric 1 controller loads the pre-programmed G-code, setting exact cutting speeds, feed rates, and tool paths. Roughing passes remove large amounts of material quickly, while finish passes bring the part to its final tolerances, often within just 5 microns. It's the kind of precision that would have seemed like science fiction to machinists just a generation ago. Whether it's aerospace components, medical implants, or automotive parts, the CTX Alpha 450 is the machine modern manufacturers trust. Impressive, isn't it? There's an old saying in the steel industry, forged metal is living metal. And nowhere does that philosophy come to life more dramatically than at Sorel Forge, one of North America's most respected heavy forging facilities, located right along the St. Lawrence River in Quebec, Canada. Sorel Forge has been crafting high-performance alloy steel components for over 125 years. Today, the forge produces some of the world's largest open-die and closed-die forgings, serving industries ranging from oil and gas, nuclear energy and aerospace, to marine and power generation. Their forgings can weigh anywhere from a few pounds all the way up to 300 metric tons. What makes Sorel Forge truly special is their command of exotic alloy steels. We're talking about chrome moly steels like AISI 4340, nickel chromium molybdenum grades, stainless steel alloys, tool steels, and even specialty grades developed to customer specification. The process begins in the electric arc furnace and ladle refining station, where raw materials are melted and chemically adjusted with precision. The molten steel is then cast into massive ingots. These ingots are reheated in gas-fired soaking pits, brought to forging temperatures between 101 to 250 degrees Celsius, before being worked under hydraulic presses delivering forces up to 10,000 metric tons. Each forging stroke compresses the grain structure, eliminating internal voids and creating a dense directional fiber flow that gives forged parts their legendary toughness and fatigue resistance. After forging, parts go through controlled heat treatment cycles, annealing, normalizing, quenching, or tempering, tailored to meet precise mechanical property requirements. Have you ever held a beautifully crafted gold chain and wondered, how on earth did they make something so delicate, so perfectly uniform? The answer lies in one of the most fascinating closed-loop manufacturing processes in the world: industrial jewelry production. And today we're going inside a state-of-the-art facility producing machine-woven chains and bracelets from 585 and 750 gold alloys. Jewelry production is a fully closed manufacturing loop, starting from alloy casting and ending with a polished, finished piece. Here's how it works. Step 1 is alloying and casting. Pure gold is melted together with precise proportions of silver, copper, and zinc in a controlled induction furnace. The molten alloy is cast into bars or rods, then passed through cold rolling mills and wire drawing machines, gradually reducing the metal to the exact wire diameter required for chain weaving. Wire diameters can be as fine as 0.3 millimeters for ultralight chains. Step 2 is machine weaving. Automated chain weaving machines, some capable of producing 12 to 20 meters of chain per minute, interlink individual wire loops with extraordinary precision. Machines like the Comes or Cittadini systems can produce over 40 different chain styles: rope chains, Figaro, curb, box, and the elegant Venetian weave, all entirely automatically. Step 3 is soldering and annealing. The chain passes through a continuous soldering oven where each link is fused shut using a gold solder, then annealed at controlled temperatures to restore flexibility and workability. After weaving, chains move to tumble polishing barrels filled with stainless steel burnishing media for 4 to 8 hours, emerging with a brilliant mirror finish. Diamond cut machines then facet selected links for sparkle before final quality inspection under 10x magnification. From raw gold bar to gleaming bracelet, every gram accounted for, every link inspected. That's the artistry of modern jewelry manufacturing. Have you ever stopped to wonder, how exactly is a shipping container made? Let's go inside a modern container manufacturing plant and find out. The foundation of every shipping container is Corten steel, also known as weathering steel, or ASTM 588 grade. This high-strength, low-alloy steel is specifically chosen for its outstanding corrosion resistance. A standard 20-foot dry container, known in the industry as a TEU 20-foot equivalent unit, requires roughly 2.2 metric tons of steel. A 40-foot container uses approximately 3.8 tons. The steel arrives at the factory in large coils, which are then processed through automated cut-to-length lines. Step 1. Steel preparation. Large steel coils are fed into decoiling and leveling machines, which straighten and flatten the material before it's cut to exact panel dimensions using hydraulic guillotine shears. Sidewall panels are typically 2 millimeters thick, while the floor cross members, which bear the weight of cargo, are cut from heavier 4 to 6 millimeters plate. Step 2. Corrugation pressing. The flat steel panels are fed into massive hydraulic corrugation presses, machines that apply up to 2,000 tons of force. Corrugation increases the panel's moment of inertia, making it far more resistant to bending and racking forces than a flat sheet of the same thickness. Step 3. Corner casting and framing. The 8 corner castings, the thick, oval-holed fittings at each corner of the container, are made from high-grade ductile iron, cast separately, and then precisely positioned and welded to the main frame. These castings are ISO 1161 certified, allowing containers to be stacked up to 9 high and locked securely to ship decks and cranes worldwide. Step 4. Assembly and welding. The container takes shape on a dedicated assembly jig. Robotic MIG welding systems lay down continuous, full penetration welds along every major joint. Manual welders follow behind for corners, seams, and detail work. Weld quality is checked with visual inspection, magnetic particle testing, and, on critical joints, ultrasonic testing. Step 5. Flooring. Traditional containers use tropical hardwood flooring. typically apatong or karuing, a dense, moisture-resistant wood that can handle forklift traffic and heavy concentrated loads. Each floorboard is bolted to galvanized steel crossmembers spaced approximately 400 millimeters apart. Step 6. Surface treatment and painting. The assembled container structure is first shot blasted, literally bombarded with steel grit at high velocity to remove all scale, rust, and contamination from the metal surface, achieving a SA 2.5 cleanliness standard. Then it receives a full coating system, a zinc-rich epoxy primer followed by an intermediate coat, and a polyurethane topcoat in the customer's specified color. Total dry film thickness typically reaches 200 to 300 microns. Step 7. Door fitting and sealing. The container doors, with their heavy-duty cam lock rods, rubber compression gaskets, and reinforced hinges, are hung and adjusted for a weather-tight seal. A finished container must pass a water tightness test before it ever leaves the factory. A major container factory can produce 500 to 2,000 containers per day, with a total output of over 1 million TEUs per year. Each container is built to ISO 668 standards and must carry a CSC safety approval plate certifying it for international cargo transport. Here's a question for you. How do you bend a steel plate that's nearly 2 inches thick into a perfect circle 6 meters across? The answer is a machine called the MH365 I-plate rolling machine, and watching it work is one of those things that reminds you just how extraordinary modern manufacturing really is. The MH365i is a 4-roll CNC plate bending machine. That 4-roll design is critical. Older, simpler plate rolls use 3 rolls. But with 4 rolls, the machine can grip and pre-bend the leading edge of the plate from the very start. No need to flip the plate or make multiple pre-bending passes. Everything happens in one smooth, continuous operation. Here's how it works. The plate is fed into the machine and gripped between the top roll and the bottom roll. 2 side rolls, positioned below and to either side of the top roll, then push upward against the plate, applying a carefully calculated force that causes the steel to yield and bend. The CNC control system, this is where modern technology really earns its keep, continuously monitors the bending radius in real time and makes micro adjustments to the roll positions, ensuring the curve stays perfectly consistent from one end of the plate to the other. Achieving a finished diameter of 6 meters with a 50 millimeters plate requires precise calculation of springback, because steel always tries to return to its flat shape after the force is released. The CNC system accounts for this automatically, applying a slightly tighter bend than the final target, so that when the force is released, the plate springs back to exactly the right diameter. The result is a rolled cylinder, perfectly round, perfectly consistent, ready to be welded into a finished component.